Welcome to another video on random variables. In this video, we're going to be talking about the mean and the standard deviation of a random variable. Really important topic and actually super easy to understand. Now, before we get too deep into it, let's talk about the law of large numbers. Now, if you remember, we actually use the law of large numbers to understand probability. We said that the true relative frequency, the true probability of an event will only be seen in the long run after a large number of trials. So if we know that, there's a 50% chance of tossing a coin and getting a head, but really what that means is if we toss 100 coins, we're not necessarily going to get 50 heads and 50 tails. It means in the long run, after many tosses, only then will we see that 50%. Well, this applies to means as well, as a mean is nothing more than the relative frequency. Okay, let me explain. So LeBron James has a scoring average of 27.3 points per game. That's his mean. That's how many points we expect him to score in the long run. So what we did was LeBron has played hundreds and probably thousands of basketball games, and over the course of many games, night after night, he has a certain number of points he scores, but his mean, his average, is his long run relative frequency. Another example is Mr. Princhak's student's average AP score is 3.7. I've had many students sit down and take the AP stats test, and over the long run, over many students, the average score is 3.7. Now, you can't even score 3.7. You can get a 3, you get a 4, you get a 5, you can get a 1, you can get a 2. But after looking at many students, the average in the long run is a 3.7. So the law of large numbers applies to means as well, because that's all the mean is. It's the average in the long run. Let's talk a little bit more about LeBron to really kind of make sure that we understand this. So let's let P be the number of points he scores in a game, right? That's a random variable. How many points is LeBron going to score? The outcome is a numerical value, and that would probably be considered discrete because he can't, in a single game, he can't have a decimal amount of points. And, it's not like it's unlimited. Maybe LeBron is kind of known for never scoring 0 points, but I guess he could score 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, but it's not like that number's going to go up towards infinity. All right, so let's just say we look at 5 games and 5 games only. Well, we would simply add up, to find the mean. Actually, I have the wrong symbol there. The mean would be X bar. There we go. So the average would be taking his points over the 5 games, 21, 18, 24, 29, 32, adding them together, got 124 total points, dividing that by the 5 games he played, and we get an average of 24.8 points per game. That would be his mean. But that's not the long run. 5 games is certainly not the long run. So if you're only looking at a sample of 5 games, that would be known as a statistic. Remember, statistics come from samples, and that's why we'd be using that symbol X bar. Okay, but what's his true mean? Well, LeBron's true mean could only be found if we look at a large number of games. Now, to be honest, for LeBron, this is still ongoing because he's still playing, but his true mean would be only found after not 5 games, but a large number of games, which he's certainly played so far. So if we look at all of the many games he's played so far, divided by the total number of games he's played so far, we'd get an average of 27.3 points per game. Now for this, we're going to use a different symbol, mu, because this would be, up to this point at least, this would be his true mean. This would be known as a parameter. It is the mean of all his games, not just 5 or 6 or this season or last season or the last 10 games. It's the average of all his games. So that's why we got to make sure that we understand, first off, how the law of large numbers plays into how to get that number, but also understand that there's a different symbol we use for a sample statistic. That's going to be X bar. That's a value coming from just a certain number of games, like 5, versus a parameter, which we use that symbol mu. Mu is the mean of the entire population, and that's because we're looking at a large number of games, like all of them. So the true mean is found after a long repetition of a random variable. All right, so let's just dive a little bit more into that exact definition of a mean. It's also known as an expected value. So the mean of a random variable is the average value of that random variable if it was repeated a large number of times. So hopefully by now we know what a random variable is. A random variable is a variable that can take on a numerical value. And if we think about the average, if that random process was repeated a large number of times, the mean of that, the average of that would be, well, the mean. But this is also known as the expected value. You're going to see a lot of times we'll call the mean an expected value. Because think about it like this, right? The mean of any variable is simply what we would expect that variable to be. LeBron's mean is how many points we expect him to score on any given night. So if LeBron has a basketball game tonight, I'm going to expect him to score the 27.3 that's his mean. Now, will he? Of course not. You can't even score 27.3 points in a single game. But because that's what he's averaged over many games, I would certainly expect him to be somewhere around that tonight. And that's what we call a mean and expected value. Now, obviously, if you're thinking about this and connecting this to what we've already learned, LeBron could score more than his mean. He could score less than his mean because, well, the points he scores in a game varies. So, of course, with a mean comes a standard deviation. So we might expect a certain value. Like we might expect LeBron to score 27.3 points tonight, but the actual result of the game is probably going to be something more or less than that. Now, since LeBron is a fairly consistent player, we would probably assume his standard deviation is pretty low, whereas a player who is very inconsistent, sometimes he scores 0 points, sometimes he scores 60 points, that's going to be a very large standard deviation. But LeBron's being a very good basketball player, he does typically score in the upper 20s, so he's actually going to have a very low standard deviation. But with any mean comes a standard deviation as well. Now, let's talk about symbols real quick. Remember, mu is the symbol for the mean of the entire population, which would be the many times that the LeBron has played, or the many times that the random variable has been completed. And then the symbol for standard deviation is sigma. That's the standard deviation of the population. All right, so let's look at a specific example here and see if we can understand this, not just looking at LeBron anymore. So the number of tickets purchased by a customer for a musical performance at a certain concert hall could be considered a random variable. The table shows the relative frequency distribution for the number of tickets purchased by a customer. So let's let T be the random variable for how many tickets a customer might purchase for a particular concert. 1, 2, 3, 4, 5. Those are our outcomes, definitely discrete, and we see the probabilities attached to it. So if I said to you, okay, the phone rings, a customer is about to purchase some tickets. How many tickets do I expect that phone call to sell? Now, I haven't answered the phone yet, but what do I expect? Well, the mean would be what I expect, right? That would be the mean number of tickets purchased by a customer. So if we were allowed this random thing to go over and over and over, right? Person calls, purchase a ticket. Person calls, purchase tickets. Person calls, purchase tickets. You know, obviously we're going to see lots of 2s. Selling 2 tickets is very common. We're going to see occasional 1, occasional 4. Very rarely, not to say very rarely, but every now and then we'll see a 5 and maybe a 3. But obviously we're going to see lots of 2s. But if we were allowed this random process of somebody calling and purchasing tickets to repeat itself many times, the average number of tickets sold would be the mean. So the mean number of tickets would be the average number of tickets sold per person after a large number of people bought tickets. So again, really to reiterate this, if we allowed this process to repeat itself, maybe the first phone call, 2 tickets. Second phone call, 2 tickets, then 1 ticket, then 2 tickets, then 2 tickets, then 3 tickets, then 2 tickets, then 1 ticket, then 2 tickets, then 2 tickets, then 2 tickets, then 2 tickets, and then 5 tickets, and then 2 tickets. If we were allowed this process to repeat itself many times, a large number of times, the mean, the expected value would be simply the average number of tickets sold per customer. Simple, right? So now the next big question is, all right, I think I understand what this mean represents, but how the heck do I get it? Well, it's actually quite an easy formula. So here it is. The mean or the expected value for discrete random variable x is, now got to be super important to make sure I emphasize that this formula can only be used for discrete random variables. It's actually a pretty easy formula, even though it looks a little bit ugly. So what you do is you take each individual outcome, that's what I'm calling xi, each individual outcome, multiplied by its probability. So take each outcome multiplied by the probability of it occurring, add all of those together. Add all of those together. And boom, you got your answer. That's it. So in simple terms, the mean is the sum of each outcome multiplied by its probability. That's it. Now, make sure you understand proper symbols. So first off, we use the symbol mu. That's the mean of a population. And that's what we're doing here. We're looking at many trials, not just 5 or 6. If we stopped at 5 or 6, that would be an X bar, not a mu. And then we do use this little subscript right here. And we typically use the capital letter that is the random variable. And generically, that's just an X, right? So that would be the mean amount of that random variable. All right. Now, always make sure you know how to explain what this value is. And keep in mind, if we were to repeat the random variable a large amount of times, the mean would be blah, 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 right? All right, so let's go back and look at our example. Well, actually, real quick, let's talk about standard deviation as well. Now, I want to emphasize that the formula for mean might look a little bit ugly, but it is so easy to use. Just outcome times probability, add them all together, so simple. The formula for standard deviation is a little bit uglier. Let me show you. All right, so here's how we find the standard deviation of the discrete random variable. All right, we start off by taking the difference between each outcome and the mean. Then we square that difference. So we're going to take an outcome minus its mean, so you do have to find the mean first, square that outcome, multiply that by the probability, and then add all of those together. A little bit more complicated, I know. Then the number inside the square root, this number that is inside the square root, that is known as variance, okay? That is known as the variance. Once you take the square root of all that variance, that's that giant square root we see here. Boy, that's kind of getting ugly. Sorry about that. The square root of the variance, that is how you get back to standard deviation. So good news is, in a couple moments here, I'm going to show you how you don't ever have to use this formula. Your calculator could do it all for you, but it's a matter of taking each individual outcome minus the mean, square that value, multiply it by its probability. Repeat that for every individual outcome, add them all together, that's your variance, square root all of that, and then you get the standard deviation. All right, let's show how that's going to be done in a specific problem, and then we'll actually show you how your calculator can do it all for you. So back to the problem about the number of tickets sold. So again, T is the number of tickets purchased by a customer for a concert. All right, how do we find the mean? This is so easy. Each outcome times its probability. 1 times 0.2, 2 times 0.45, 3 times 0.1, 4 times 0.20, 5 times 0.05. Add all of that together, boom, there is your mean. Notice I put a little subscript of a T there. The mean of the number of tickets sold is 2.45. So in the long run, we would expect to sell 2.45 tickets per customer. So if phone's about to ring, I would expect them to purchase 2.45 tickets. Obviously, they can't do that, right? It's a mean, right? It's an average in the long run. They cannot purchase that. They could purchase 2, they could purchase 3, they could purchase 4. They can't purchase 2.45, but it's the same thing as LeBron can't score 27.3 points in a game tonight. It's an average. It's a mean in the long run, so it's okay to be a decimal. But of course, the number of tickets sold could vary, right? Could be a little more, could be a little bit less. So of course, the standard deviation comes in as well. So here's how we do standard deviation. We take each outcome minus the mean. So there's the 1 minus 2.45 squared times its probability. Then we're going to do it again. Outcome of 2 minus the mean squared times its probability. Do it again. Outcome 3 minus the mean squared times its probability. Do it again. Outcome 4 minus the mean squared times its probability. And then one more here, outcome 5 minus its mean squared times its probability. Add all that together. The number inside the square root is known as variance. But then when you square root all of that variance, you get the standard deviation. And that turns out to be 1.61. So the average customer is expected to purchase 2.45 tickets, but that number could deviate by plus or minus 1.161 tickets. Now, once again, remember, standard deviation could be a little bit more or a little bit less. So we could sell a couple more tickets, we could sell a couple less, okay? Not too bad. Now, how do I do all this on the calculator? Because most kids don't want to do all this work. Even though doing the mean is not that bad, standard deviation could get a little hairy, a little time consuming. So here's how you do it on your calculator. Really simple, but boy, oh boy, please pay attention and practice. First, we have to enter the data into the calculator. So we're going to hit the Stat button, and then we're going to go to Edit right away. In list 1, we're going to put our outcomes, 1, 2, 3, 4, 5 tickets. In list 2, we're going to put the associated probabilities, 0.2, 0.45, 0.1, 0.2, 0.05. Make sure the proper probability is across from the proper outcome. Once that's done, pretty simple, just exit out of there. Then you're going to hit Stat again. This time slide over to Calc in the middle and select one variable stats. Now here's where there's a key difference you really got to pay attention to. When you click on the one variable stats, the first thing you got to do is tell it where the outcomes are. That's your list. The outcomes are in list 1. And then normally we would leave the frequency list blank, but because the outcomes have a frequency attached to them, so just to go back and explain that, for example, an outcome of 2 only happens 45% of the time, so we need to take into account that frequency. So that's why we have to add the frequency list as list 2. Then go ahead and hit calculate. And you'll get everything you need. Now right at the top is the mean, the 2.45. I hate the fact that it calls it X bar. It's actually not. I've put several phone calls into Texas Instruments. I wish that they would change that to a mu. But the problem is the calculator doesn't necessarily know if you're talking about a sample versus a population, but we know we're looking at the long run relative frequency. Many, 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 many trials, not just a set amount. So please make sure we label this as mu. The average number of tickets in the long run is 2.45. And then we're going to come down here for sigma, the standard deviation. There's that value that we got for sigma. The standard deviation of the number of tickets sold. And I always recommend going with 3 decimal places, 1.161 there. So that's exactly how I got those 2 values. All right, I mean, that's it. That's really how simple it is. The most important thing is you understand what the mean is. It's the average value in the long run for that random variable. So what's the average if that random variable is repeated multiple times? And that value could, of course, deviate, and that's why we have the standard deviation in there as well. So please make sure you understand all of that. And just one more comment I want to make on parameters. The mean and standard deviation of a random variable are known as parameters. They do not come from a sample. If we just said, hey, let's sell 5 customers. Let's just look at 5 customers, find the mean, find the standard deviation. Yes, that would be statistics because it's coming from a sample. That would be X bar and S. But when we're looking at the mean and standard deviation of an entire random variable, we're not just talking about looking at 5 trials or 10 trials. We're talking about looking at many, 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 many trials. So they are more of a theoretical idea of what the mean and standard deviation would be after a large number of trials. We would consider this the population. So they both must be interpreted using correct units and in context to the specific situation they are coming from. They must be identified using those proper symbols. So that's why don't just say 2.45 and 1.161, right? The mu, the mean in the long run, the average number of tickets sold is 2.45 tickets, but that average could deviate, and that's where the standard deviation comes into play. Could be a little bit more, a little bit less, and that's the 1.161 tickets that the average could go up or down by on any given customer. All right, hopefully this was a quick and not too painful video on finding the mean and standard deviation for a random variable. There will be some more videos if you're looking for more practice or more examples, so definitely stay tuned.